Okay, so let us get back to our equation that we were discussing in the previous lecture. So, this is the equation for GS, which depends on so many factors: H, which is the heat loss coefficient; A, the radius of the crystal if it is considering it is cylindrical; Ks, which is the thermal conductivity of solid; and Tm minus T naught, which is the difference between the melting temperature and the room temperature or the ambient temperature. So, these are the factors. Now, let us get back and try to recollect what we have said so far, and we will solve a problem onto this in just a moment. So, now let us look at the slides a little bit. We note that the growth velocity R is dependent not on absolute thermal gradient, but on difference between KSGS and KLGL. Absolute thermal gradients can be controlled independently of the growth velocities. So, even if you have the same R, you can have two different combination of GS and GL that can give you the same growth velocity. So, absolute thermal gradient can be controlled independently of the growth velocity. Growing good crystals require that the temperature gradients be high, which I already mentioned, and the growth rate be low enough to match the theoretical growth velocity. We also found that GS, which is this equation, can be calculated by experiment or heat flow equation. In this particular case, it was obtained using a heat flow equation, the details of which we have not discussed, but this is the final form of the GS value, which is the thermal gradient in the solid. For metals of high melting point, where Tm minus T naught is large, thermal gradients of high values can be obtained. So, that is again something that is that you can understand when you look again at the equation. GS is proportional to Tm minus T naught. Compare the Tm minus T naught for aluminum versus let us say steel. So, you know that steel is not a good example because steel is alloy, not a single component material. So, let us say we are talking about iron. So, iron will have 1500 plus melting point. On the other hand, the melting point of aluminum is 660 Celsius. So, Tm minus T naught for iron will be much larger, and therefore, you can get much larger thermal gradient of solid in iron than in aluminum. For lower melting point metals, some other cooling methods can be employed. Now, let us say Tm is fixed, but T naught is something that you can change. How can you change T naught? You can reduce by some cooling mechanism. You can make it cryo, less than 0 or sub-zero temperature. That way again you can increase the value of Tm minus T naught, and so still you can get high GS value. In practice, the growth velocity of 1 to 3 millimeter per minute can be attained. Now, having said this, let us try to solve a simple equation, some simple problem based on this. We talked about the floating zone technique, which is for growing single crystal where there is no mold. So, you can see that it is a very sophisticated technique which does not require mold. It is not in contact with any outside surface, and therefore, heterogeneous nucleation will not take place, and so there will not be nucleation taking place all around the walls. Now, in a floating zone technique, we are trying to solidify aluminum, and the radius of the crystal is 0.3 centimeter. Coefficient of heat transfer is given, and you are also given values of the specific heat of the solid aluminum, molten aluminum, heat of fusion, and all the values that you would need. Now, the question is, how will you find out what is the maximum temperature gradient achievable at solid liquid interface in the solid? First, let us look at the maximum temperature gradient achievable at the liquid solid interface in the solid. Remember, we are always talking about the thermal gradient at the interface, whether it is in the solid or liquid, but at the interface. So, let us look at what is the maximum thermal gradient that you can obtain in solid. So, what we need is for the solid, first let us look at solid. So, this is the equation we have already derived over here. You have to look at this equation. Now, the question is asking for maximum thermal gradient in the solid. We have already seen that these are parameters that are already given, you cannot change that. Now, if the material is given, Tm is fixed, and assuming that and in fact T naught is also given, so this is also fixed. So, the maximum or the only value that you can calculate for GS is by taking all the values that are already given. You cannot change it, given that Tm is fixed, T0 is fixed, H and AKS are all fixed. So, you will get only one value, and if you put in all the values over there, you would see that it comes out to 78.6 degree Celsius per second. So, this is for GS. Now, what about GL? We want to find out what is the maximum value of GL. Now, what will happen if you keep increasing GL? If you keep increasing GL, you remember it is a negative term, so the rate growth velocity keeps decreasing. So, there will reach a point where growth velocity becomes 0. It can never become negative, you cannot come down or you cannot start melting. So, the highest GL would be the condition where Ks GS is equal to KL GL, meaning the rho SH R term has gone to 0. Basically R has gone to 0, and therefore rho SH R term has gone to 0. Therefore, Ks GS is equal to KL GL, and from here you would say that GL is equal to Ks by KL into GS, which is just basically multiplying GS by a factor, and therefore this factor happens to be 0.53 by 0.2 into 78.6, and you get 208.3 degrees Celsius per second. It's a growth, it's the thermal gradient. So, sorry, this is my bad. Again, let me recorrect it. It's a thermal gradient. It's not per second, it is per centimeter. The units, if you check properly, it will come out to degrees Celsius per centimeter. It's a thermal gradient. We are not talking about the heat rate or temperature rate. So, it is degrees Celsius per centimeter, 78.6 degrees C per centimeter for GS, and GL maximum value you can get is 208.3 degrees C per centimeter. So, that solves our first part of the problem. Now, let us look at the second part of the problem. It says, would these temperature gradients which we have calculated just now, which are 78.6 and 208.3, will this temperature gradients be significantly different at a typical crystal growth velocity of 5 into 10 to the power minus 5 centimeter per second. So, in the second part you are being given the growth velocity R, and then you have to calculate what is going to be GS and GL, or basically you have to comment on whether GS and GL would be very different. The easiest way is, why not calculate GS and GL again, given that we already have the R value, we already have rho SH R, so why not calculate all those. So, let us calculate GS for this given growth velocity, but we see that GS does not depend on R, which means that GS would remain same that we had calculated earlier, 78.6 degrees C per centimeter. What about GL? If GS is given, R is given, then GS would actually depend on R from the first equation that we talked about in terms of single crystal growth. So, this will be this would be the equation that will give you the value of GL, and when you put these values over here, what you would find is that GL comes out to 208.23 degrees C per centimeter. Now, you look at these values and compare it with the values that we obtained earlier. So, GS remains same, of course, because it does not depend on R. GL, which is a imposed value which does depend on R, is actually not very different at a typical growth velocity of 10 to the power minus 5 centimeter per second. So, our answer would be that no, the GS and GL, the thermal gradients, do not depend much or do not vary much when we are talking from the maximum value when we are talking about a typical growth velocity. And why is that? The reason is that GS does not depend on R, What about GL? GL does depend on R, but then GL is not much affected by value of when R is very small. So if the R value is very small, this whole term becomes almost negligible, and what you have in GL is effectively Ks GS by KL, which is equivalent to our maximum gradient, thermal gradient that we were obtaining. So this value does not make much difference to GL, and therefore the answer is that whenever you have a slow growth rate, which is the typical growth rate velocity, it will not influence the GS and GL at all. Now at this point, let me add another question to this. You have all the conditions given. Now if someone asks you, how can you increase GS and GL even further, what would you do? Again we will come back to this. You know that Ks cannot be changed. Okay, so first let us go back to first the GS, because GS is the one independent. So here we cannot change Ks, we cannot change Tm, but we can make a difference to some of these quantities. H, heat loss coefficient, meaning if you start or if you allow more heat loss to the furnace environment, then this quantity becomes larger, so GS can become higher. A is a radius. If you decrease the radius, then again GS can increase, but then that would also imply that you are getting a very thin single crystal. Beyond a point it may not be meaningful, so you may not like to make much change to this. We already said Tm is not something that you can change, but T0 is something that you can change. You can put some additional cooling mechanism, so your ambient temperature is no more T0, but let us say some minus 50 degrees Celsius or minus 100 degrees Celsius. So if you put an additional cooling mechanism, T0 can be reduced, and this factor can become large and GS will become large. And once GS becomes large, then GL will also become large. So these are the ways that you can increase both thermal gradients of solid and liquid near the interface. So that is all we will talk about the heat flow in single crystal. Next we will talk about the heat flow during the solidification of castings and ingots. In most casting and ingot making process, what you will see is that heat flow and solid liquid interface are not controlled. You remember in the single crystal growth we were talking about the controlled rate of interface movement, and that is what allowed us to have single crystal, but that is not the case when we are talking about the ingot making or the castings. For example, if you are making a sand cast mold and you make some casting out of that, over there you are not controlling at what rate the interface should move, not even at what rate the thermal gradient should move. All those are automatically controlled, adjusted, and hence what we get is polycrystalline materials, and therefore it also means that you do not have to have a very small growth rate you can have very large growth rate. In fact, you can get a very large casting in matter of few minutes, but that was not the case for single crystal. In the castings and ingots, the amount of heat which we have, which is the specific heat as well as the heat of fusion of the solidifying metal and the cooling solid, it must pass through a series of thermal resistances and to the outside of the mold, and only then your heat flow process has completed. This itself is a very complex, or it involves a lot of you can say different heat flow equations or thermal resistances. You have to take into account several conditions to formulate such problems. Thermal resistances across the various interfaces and the liquid and solid should also be considered. All in all, the problem that we are describing here becomes physically and mathematically very complex, and it will become even more complex if we are talking about complex geometries. If we are talking about, let us say, just a simple rod, then this can still be a tractable problem, but if we are talking about let us say engine head, over there you have somewhere convex shapes, somewhere concave shapes, and then the geometry also adds to the complexity of heat flow, and in that case you may need some computational approach, meaning you may have to have a finite element method kind of solution to find out the actual rate of heat flow. But we are never happy with that, we always want to simplify the assumptions and find some analytical solutions, and certain so that is what we will do over here. We will have some certain simplifying assumptions to be able to get to some simple solutions under some simple conditions. So what are those simple conditions we will look at. But before that, let us talk about what are the different, in a very general condition, what will be the different layers that through which the heat has to flow, which makes it so complex. There will be liquid, and again to make things simple, we are assuming a single dimensional geometry. Thereafter you will have a layer of solid. So this is the solid which has solidified from the liquid. Beyond that there will be a mold, and outside the mold you will have the air layer. So the heat has to go from all the way from liquid to solid to the mold and into the air. So that is the way the heat flow will take place. And if we were to draw the temperature plot, it may look something like this. So this is, let us say, the ambient condition T naught. In the mold it will rise to some place, then there will be an interface resistance at the mold and solid, then in the solid there will be temperature rise, and there may even be a temperature rise in the liquid. And in fact what I forgot to draw here, let me draw it, there may even be interface resistance at the mold air interface. So this is how a most general condition for casting would look like. Now you can see you have to take into account heat flow from here to here by conductivity, then by thermal resistance, again by conductivity, then there is thermal resistance. So there is lots of conditions involved. So there is a temperature drop over here, there is a temperature drop over here, and so on. The way I have drawn, you would note a few more points. One is this, that the curvature is decreasing from left to right. The temperature profile that I have drawn, the curvature for that temperature profile is decreasing. It is higher here, it is becoming smaller and smaller as we go from left to right in the solid. However, when I have drawn it in the mold, it is quite inverse. Here the curvature is increasing when we go from left to right. So this is something we will not talk right now, but I want you to think about it a little bit, and we will come back to it in one of the later lectures when we discuss in more detail about the heat flow. But you will see that this is always the case. In the mold you will always have the curvature increasing, and in the solid you will always have the curvature decreasing. So this is a complex state. Now let us look at one of the simplifying conditions, and the first of these simplifying conditions is called insulating mold. Now as the name suggests, the mold is insulating, meaning it has much higher, you can say, thermal resistance. So this is the insulating mold condition, one of the simplifying assumptions that we will first look at. Where are these conditions valid? These are valid in, for example, sand mold casting. This is also valid investment casting. So, see how we are able to relate what we know about the fundamentals to the actual processes, and this is one place you can directly see, although even the earlier ones where that we have talked, like the single crystal etc., over there also you are able to directly relate it with the real technique or the actual technique. So, this is the insulating mold condition. Now, as the name suggests, metal is a good conductor here and it is considered even you can say very good conductor in terms of these approximations, is a good conductor of heat than mold. And because of this, solidification rate is decided by mold mainly. So, this is the implication of insulating mold. When we have an insulating mold, we are assuming that metal is a very good conductor and much better than the mold, and therefore, the solidification rate is controlled or decided by only the mold properties, mold characteristics, and as you will see in the equation also that we will derive, the metal characteristics do not come into picture. And to end today's lecture, let me just draw a temperature profile that you would see in insulating mold condition. So, this is for the most general condition. How would the temperature profile look like for insulating mold condition? In here, so this is the temperature profile that we will have for a insulating mold condition, where this is the liquid, this is the solid, and this is the mold. Now, as we have already pointed out and we will discuss in more detail in the next lecture, that all the heat that comes into solid gets transferred to the mold, and therefore, you do not see any temperature drop over here, because solid is being assumed to be a much better conductor than mold. All the heat will get transferred into the mold, and all the temperature drop is taking place in mold. And along with that assumption, we are taking couple of more assumptions that we will discuss in more detail, but just to give you a brief idea, we are assuming that temperature of liquid remains same, which is at the Tm, so no superheat over here, and we are assuming a semi infinite mold. So, these are two more inherent assumptions which we have not explicitly mentioned, but it is also inherent in this that we use when we derive the analytical solution. So, with that we will end today and we will come back to this point in next lecture. Thank you.